This is Lake Berryessa in the Napa Hills north of San Francisco, California. The white dot coming into view on the far shore is Mike Arnold's AR-5. The black dots are cows. Engine failure.
You don't see any marks back there, do you, Andy?
So you thought you remembered actually coming
I
down
actually
here?
touched here and then hopped over the ditch, but oh yeah, there it is.
Mike was coming home from a visit with his friend and fellow composite builder Andy Green when he decided to make a low-altitude, high-speed pass over the smooth surface of the lake.
So when you're coming around down here?
I was actually out over where that houseboat is when it quit. And then made a big wide turn around here. I thought I would never reach that shore over there. Yeah, there it is. That's the first hit. Well, the gear was obviously in good shape after this one.
Yeah.
And it just was hitting that high spot over there that tore the gear off.
Mike had tried to bounce it from here to the other side of that low, wet-looking spot out there.
Oh yeah, I would have just stuck, spiked me in there.
The AR-5 had flown over 70 trouble-free hours in the last year and a half, so it was a big surprise yesterday when it suddenly lost power. It was just 5 weeks ago that the airplane set a new world speed record.
Yeah, you make a good formula pilot.
Running white back there.
213.18 miles per hour on 65 horsepower. Hot stuff. But the only thing hot today is the weather. It's over 100 degrees out here. The ground has been gradually descending towards the low, wet depression he'd tried to bounce over. It turned out to be pretty soggy, but the real problem was the 3-foot rise on the other side of it. A foot and a half below the top of the rise, the main gear hit. The impact broke both axles and bent the 2 steel gear legs back about 30 degrees, and bounced the airplane back up into the air a second time.
94 paces to the... That's a long hop, 94 paces.
Let's go.
Yeah.
Just another foot or so and he would have been all right. The airplane was flying again here and fully controllable, so Mike was able to flare out for the 3rd time before the final impact. When it hit the last time, with the landing gear bent back and the wheels askew, it went over immediately onto its nose, and in a remarkably short distance, skidded to a stop.
So you were flying again right here.
The deceleration pulled Mike's glasses off. They were thrown down behind the rudder pedals when the nose hit.
That's 94 and 65. That's a lot. 94 paces from the first bump to the second bump, and another 65 to stop.
A preliminary inspection right after the crash had shown no visible damage to the primary structure, and the wing tips showed no signs of having touched the ground. The gear folded up just like it was supposed to without wrecking the wing.
I'd say the airplane's in fine shape.
I would say I was a real lucky guy.
Mike had worried about such an off-field landing accident since he started the design, fearing that the small wheels and close-fitting wheel pads would vault him over on his back on any surface but a paved one. So he was understandably relieved that things turned out the way they did. It would have been better to have cleared the top of the rise, of course, but the damage was relatively minor. The AR-5 will fly again. The cowl got crunched, and there were suspicious dark trails coming out from the exhaust system vents, but they turned out to be dirt blown through when the nose hit the ground.
No, just keep it straight, if you will, Max. Right. See if I can set higher.
The big challenge now was to get it apart and trailered out of there without doing any more damage to it. The airplane is made of fiberglass and epoxy over styrofoam, in the manner of Burt Rutan's Very Easy and Long Easy designs. While it's a very rugged kind of construction as shown by the various examples that have crashed, its fiberglass skins are quite thin and can be easily dented enough to crush the foam core underneath. All loads must be spread out carefully. The broader the back, the better. It won't take pointed loads. The wings are being placed on styrofoam and particle board pads, shaped to conform to the airfoil. Now, maybe we can find out what happened. Mike had gone to full throttle just a moment before the engine suddenly lost power. It didn't quit altogether, at first. It seemed to have gone to a very weak, rough idle. And then, over the next 10 seconds or so, it slowly ground to a halt.
Brett, you might want to get a shot at all this good stuff.
Mighty
dirty. Yeah.
It's usually not this dirty in here. The cowl halves were in one piece. They were just cracked, so they were repairable. It's almost always easier to repair a fiberglass part than to start over. And now that we have the cowl off, we can begin to investigate the engine failure.
No, I think we're just about to take a look here. This came off.
The dirt had knocked a clamp off the expansion chamber insulation. That wouldn't have had anything to do with the engine failure. The major parts seemed to be where they were supposed to be. The lines weren't leaking, no fluids in the cowl. All the wires seemed to be connected.
Oh, doesn't feel real good in there. Something seized up.
Later it was discovered that a small ferrule Mike had soldered onto one of the throttle cables had come off. A bad solder on a 5-cent part had put the airplane down. 4 bolts hold the wing onto the fuselage, but there are control cables and brake lines that have to be disconnected. We don't have much time before dark, and we don't want to leave it out here tonight. We've got to get it on the trailer, but this borrowed one wasn't made for airplanes.
Boy,
I think it's going to work.
Really scary.
But it's a light airplane, and we all feel like we're in good shape. And we certainly all know what we're doing.
Okay, are we high enough? It seems like it's hung up, and we're rolling here for some reason. What's happening? Oh, there we go. Are we high enough? Yeah, go. Yeah, we're looking good. You're not going to scrape the fuse to the wing? Higher, 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 higher. Keep going. Looking good. Higher. We're about to get. Oh, got the right. Straight. We're outside straight. Going fine. I'm looking good. The 2x2 are we over? Hold on, mister. I can't hold on. We're resting the. Here, let's put it down right there. Get up from under it, Max. Are we on the fuselage? Yeah. Are we? Yeah, we're moving good. There. Oh, down back there? Yeah, we're safe so. Okay. Where are we? That was all right. We're okay. Are we? We're okay back here. Okay, so we can slide this over.
Now, with the fuselage safely on the trailer, we had to figure out what to do with the wing.
On that trailer.
Well, could we slide the tail of the airplane over to one side? No, because then the tail is sticking out.
The only solution seemed to be to find a safe place to leave it and make 2 trips. Bill, the local rancher, was kind enough to let us leave it in his front yard. We left after having made solemn promises to be back in a couple of hours to pick it up. Yeah, right. We figured we'd zip over to Andy's hangar in Angwin, drop off the fuselage, and be back before dark. It's only an hour on the freeway. There's no place on the fuselage to cradle it without every bump on the unsprung trailer punching a deeper dent into the foam cores. So the tail wheel was strapped to the board and straddled by a couple of nails. The rest of the fuselage was unsupported. At the front, it was strapped down to a board clamped to the trailer frame. It was precarious, so Mike decided to ride with the airplane. It took over an hour of the worst washboard road any of us had ever seen just to get it out to the highway. Things were getting pretty grim.
They understand that stuff. Okay, I sure appreciate that.
Arrangements were made to come back for the wing the following day. We'd had enough for tonight. There were lots more adventures left. The fuselage would be loaded and unloaded 3 more times before it finally made it home.
All right, bye-bye. Good guy. Okay, so we're going to Angwin, right? Okay, here we are, back from the mountain. What an ordeal. The engine is, and the whole setup here is just about what we had for the record attempt. I think we've changed main jets since then, but everything else is just the same. This is a Craig Cato propeller, 50 by 70 inch pitch on a 2-to-1 gearbox. Rotax makes 3 different gear ratios, a 2-to-1, a 2.24-to-1, and a 2.57-to-1. We've elected to turn the propeller higher with this 2-to-1 gearbox. It's an absolutely stock 582 Rotax, dual ignition, comes stock, 2 spark plugs per cylinder. The carburetors are stock. They're the normal Bing carburetors that are sold with the engine. In this case, as I mentioned, we have changed the jets around a little bit for the record attempt, but they're all normal everyday jets. We've fattened up the mid-range a little bit with a different needle jet. But beyond that, they're all the same. You notice that we're not using the chokes on this engine. We left the chokes on, but they're not connected. And we're using the primer system to start the engine when it's cold. And let me talk to you a little about the famous backward throttle here. We're just running the throttle linkage right straight out into a junction. And I'll show you a little bit later on what we're doing in the cockpit. Everyone is scared to death when they see this because you pull for full power instead of push. And let me talk a little bit about the motor mount down here. This is a fairly standard mount. I think I saw this set up first on a kit fox. It's a 3/8 plate that the engine is bolted to. It's shock mounted with 2 neoprene rubber mounts. The motor mount itself, you'll see in this picture, is a pretty stout thing. It's 4130 steel. You can tell that I've added a little piece down here. When I first flew the airplane, I just had this square tube without this section here. And we noticed that it was bending a little bit in the front and the back from what's called the rocking couple of this peculiar to this Rotax engine. So we stiffened it up with this reinforcement here. Added 1.5 pounds to the weight. I'm never happy about that, but that's the way it goes sometimes. Okay, one of the things every designer likes to see, no one wants to see his airplane crash, but boy, they're fun to look at when they've been pushed on hard. When the nose came down on this one, it hit the dirt and crushed the cowl, pushing it up into the bottom of the gearbox here and onto the bottom of the motor mount here. That load went directly back here and right straight up this upright. If you can follow this through here, right on through until it attached to the firewall in the front here. Okay, I want to talk a little about the cooling system. The water comes out of the cylinder head at this point, runs down through this 1-inch hose, runs right down to this splitter here. Can you see that splitter? What it's doing is it's splitting off one side and the other side into the tops of the 2 radiators. Now, where are the radiators? Let's just reveal. Here's one of the radiators right here. And we just stick this. This is just the catch tank.
it's coming out of that splitter and up into the top of this radiator, flowing down through the radiator, going out through the bottom, and into another Y underneath. We'll take a look at that later. Oh yeah, you can see that okay. Coming out of the Y here and going into, you can't see it, but it's going into the water pump on the other side. Now here's that splitter from the other side. You can see that it's coming out of this radiator, going down into the splitter, just like the other one did, and the two of them are joined now, running up here into the water pump, which is behind the baffle there. We can't see it until we take that baffle off. Okay, now we can see the water pump, now that we've got that baffle removed here. Wanted to point out to you this little vent that we had to put in at the top of the water pump. These tend to collect air up on the top and cavitate, which is not a good thing. So we vented the system permanently because, of course, we can't get behind it to crack this vent with the baffle and the exhaust system in the way. We vented it right on up to the header tank, just like we did the other vents. Okay, what we had to do to vent the top of the cylinder head was run a little vent right out of here and plug it into the top of this little aluminum header tank here. The other line that you see running out here bleeds air that comes out of the tops of the two radiators and allows it to migrate on up to the header tank. The header tank, of course, has to be the highest point in the cooling system. The way the cooling system on this installation works is all the air that comes in through the annular inlet here, that comes in on this side of this baffle, flows over the engine, provides induction air on its way through, and works its way back into the back near the firewall here and out through the radiators on both sides. No air that comes in through the front of the system on this side of the cowl can go out any other place but out through the radiators. On the opposite side of this baffle, any air that comes in through the opening up here winds up coming out through the top of this vent. So it has a separate inlet and a separate outlet just to cool the exhaust system. This little vent back here takes air out that has escaped through the back of the baffle from the exhaust system and tends to pool up here at the battery. So we put this extra little vent in here. Okay, here's the famous modified exhaust system. This is basically a stock Rotax muffler, or can as they're referred to. It's hung off these two square tubes here, which are bolted to the tops of the cylinder head. The can is a standard Rotax part. The modification starts right here. This expansion chamber, all of these connectors, all the way up into the manifold itself, we had to make over again in order to fit the thing underneath the cowl. We were fortunate to get some stainless steel bends that were approximately the right diameter. We're able to find this shape in an aftermarket jet ski exhaust system, but the diameter wasn't correct. We've taken off the insulation so that I can show you what we had to do to make that diameter correct. We had to put in a little wedge all the way through here to get that diameter close to correct, and as you can see, what that's done is it's changed this round section to a flat oval. And my suspicion is that that has reduced the efficiency of the reflected charge here, which is so essential to the performance of two-stroke engines. I think probably the engine is only producing 64 to 65 horsepower. Well, we finally got the airplane back into the shop where it was built. Can you imagine that we got the airplane in through that little door, this whole airplane? Good thing it comes apart. Once we've got it in here, we can start taking a look at the inside of the airplane. I want to show you what's underneath the cowl now. We've taken the engine off, and we had to do that in order to get it in the shop. But we put the motor mount back on so we can continue our little examination of the results of this incident, not an accident. The FAA says this is an incident. Tim, would you take that? We have a little clearer shot of the motor mount in this shot. This is the strut, of course, that carried that compression load right straight back into the firewall. And this is the diagonal or the upright that carried it up into the firewall in this area. We'll take a look at that in a minute, but while we have it right here, let's take a little closer look at how this radiator system works. Tim, can I have that? This is the radiator, and the radiator fits right into this little duct like this, and the whole unit gets bolted right up to the firewall like that. A little better than that, hopefully. Tim? This is about 23 square inches of outlet area here total for both sides, which is a fairly low ratio for an engine of 65 horsepower. Not too bad, at least. Okay, I think we've pretty much covered what we need to cover in here. Let's come around here and take a look at what's underneath here. This is the access cover for the fuel filler cap, and it's also the way that I pulled this panel off. The panel is a sandwich structure, just like the rest of the airplane. Styrofoam sandwich, fairly light. Okay, right here, I want to talk to you about how this stuff is made before we get any farther along here. This is another upper deck that we didn't use for a number of reasons. But before we even talk about how this is made, we have to talk a little about the materials it's made of. Let's take a look here. This is the famous sandwich. This is the kind of construction used throughout the airplane. It's a little different foam that we're using here, but the principle is the same. What I want to show you about this is what happens as a result of the introduction of this foam between these two pieces of fiberglass here. This is a fiberglass epoxy laminate. It's the same amount of fiberglass all the way along this edge here, all the way along both sides. But look what happens because of the addition of the foam to the stiffness of the unit. This part that has no foam in it is very flexible. The other part is rock solid. Just the addition of the foam stiffens this panel. You can make sandwiches out of all different kinds of cores. This is a craft paper honeycomb core. Makes a very nice sandwich. Fiberglass on both sides, quite stiff. This is a piece that we took out of the fuel tank. We'll show you how the fuel tank is made a little later on. It's a little different kind of foam, but the same procedure. Quite stiff. Here's the sandwich that we've talked about. It's 0.4 inches thick, fiberglass on both sides, quite stiff. And what I want to tell you about is how I make these inspection panels here. The first step would be to mark the outline of the panel on the outside and then flip it over. Now remember that at this point the sandwich extends all the way across here. It's all one piece, all the same 0.4 inches thick. The first move is to dig a trough down through the fiberglass, this fiberglass, and ditch out this foam all the way around here. So it runs from here down and back up again into this one. All this foam's gone. We carve it right down to the bare fiberglass throughout this whole area here. None of this is here, of course. And we lay up a piece of fiberglass from right here all the way down into that ditch and all the way up the other side and stop it here. All the way around we do that. When we've done that, we flip the whole thing over again and cut along that line that we've marked and pull that panel out of there. Once we've got the panel out of there, remember none of this is here yet, no flange is here yet, we're going to put duct tape all around this piece here so that when we do the next step the epoxy won't stick to this panel. Okay, we put a little duct tape here I didn't bother to put it all the way around here. I want you to notice that the duct tape is sticking up a little bit all the way around here. And the reason we have the duct tape sticking up a little bit like that is so that when we put the panel back in, which is the next step, and jig it into place with some little sticks with Bondo on all sides, holding it just exactly where we want it, the duct tape sticks up enough so that when we pack the flocks and epoxy, flocks is just cotton, basically shredded cotton, a mixture of flocks and epoxy, we're going to poke it down into this hole so it fills up any gap that we might have in there, and it will go right up against the duct tape and allow, after the epoxy has cured, allow us to push it back out of there, leaving a perfect gap. It's just how we did this, but we're getting ahead of ourselves. Let's take a look at the bottom side now once we've got the duct tape in. As you can see, the panel keeps falling out, but I'm going to hold it in here. Well, the next move is to lay up a piece of fiberglass right from my fingernail all the way over here, which forms this flange. That's the purpose of the duct tape, is to lay up the fiberglass against it so that when we pull it out, it leaves this edge here. Let's take another look here so we can see that flange. This little bit of fiberglass that we leave after we've trimmed this all up is of course, the flange that seals, that keeps air from flowing through this gap here. And after reinforcing these little edges here where we're going to put bolts through, we have pretty much finished off this inspection panel. That's pretty typical of the inspection panels throughout the airplane. Okay, well, how do we make a sandwich structure in the first place? Max and I have got a little demonstration set up for you here. You can see that we have a styrofoam block laid out here with some weights on it. This block is a Dow Chemical 2-pound density styrofoam, normal standard stuff. And on top of it here we have a little device we call the hot wire saw. This one's been around in this shop for 11 years or so. It's basically just a unit designed to stretch this wire by the use of a turnbuckle back here and a little hinge here. So when I tighten up the turnbuckle, it increases the tension on that wire. The wire is a piece of nichrome safety wire. I think it's about 40 thousandths or 35 thousandths. And let's just take a look at the template here. What we're going to do is nail this template to the side of this block. Just press some nails in through these little holes here. This template is the template that formed the tip on the AR-5, the wing tip. We use templates for wing profiles, as well as they come in all sizes. Here's one that we used on the back of the fuselage to carve the shape in that the tail cone. We'll show you this a little later. You'll see this in some stills. So let's get right on to it.
This method of wing construction, using a hot wire to cut a styrofoam core and covering it with fiberglass, was first seen in this country on the home builds designed by Burt Rutan in the late 70s. Since then, his very easies and long easies have been produced in the thousands by amateur builders around the world. Their airframes have accumulated millions of hours and have established a reputation for being safe, robust, and long-lasting. This basic method has also been used on several other more recent designs with equal success. It's a good way to make a laminar flow wing.
Max, you about ready?
So,
what we're going to do is plug this unit into the transformer, and it's a straight hookup out of the transformer right into the both ends of this hot wire. Doesn't require a lot of voltage. We run this one at about 20 volts or so. what we're going to do is hook up the hot wire right on this little wire that we have epoxied to the end of this template, and we're going to wait there for a moment. Right on the wire. Okay, are you ready to go into the wire now?
So,
Okay, right into the template. Ready, up to 1, 1, half, 2, half, 3,
not up to 3 yet. There on 3.
half,
And a half.
4, half, 5, half, 6. You want to do this kind of slow or you'll bend the wire. 7,
Not quite. Now I've got it, yeah.
half, and it's important to keep coordinated with the guy on the other end of the wire, of course.
I'm just,
8,
yeah. I don't have an 8 over here.
half, 9,
Yeah, I got it. 9.
half, 10, half. Let's come out at 11, Max. That's far enough.
Here we go.
Wait,
I've got it. 11.
11. Okay, up. It's important to keep coordinated. And we've made a hot wire cut. Pretty snazzy, huh? I'm going to shut this off. No, actually, let's go ahead and cut the bottom side here too, Max. Let's go down to about 6.
Okay.
Underneath the wire, and then straight out.
Okay.
Underneath the wire, okay, straight into the template.
Okay.
Go. 1,
And a half.
half, 2, keep it up on the template,
Yeah.
half,
3.
3, half,
4.
4, keep a little tension on the template, half, 5,
A half.
half,
6.
6, okay, straight down. Okay, we'll put the saw on the floor for a minute. Now, what we have basically here is the foam core for a wing. Nice, nice. One of the things that happens when you hot wire is the template, the metal template that's along this edge, cools off that wire a little bit, so it leaves this edge a little high. So what we do to fix that is we do a little light sanding. This is just a board with a little 36 grit sandpaper on it. And I'm just going to sand this edge down a little bit. Long stroke. And to check myself, take a straight edge and put it down, see if it wobbles. It just wobbles a little bit right here, which means this edge is a little high. That's pretty darn close. Another couple of swipes there. And I'm going to go down to this other end and do the same thing.
Sanding is a very important part of the project. Most builders sand wings with a flexible board called a sailplane spline. Mike doesn't use it, preferring the results he gets with the long board. This is the same sanding board Mike used throughout the shaping and finishing process. It's 2 1/2 inches wide and 32 1/2 inches long. The heavy grit sandpapers are contact cemented directly to the wood. The finer grit papers are cemented over this 1/8 inch thick corrugated rubber mat, which helps keep the sandpaper from clogging. Those pesky clogs are removed with a coat hanger whacker.
I'm going to do a little sanding around the leading edge here.
The movements are always the same, stroking diagonally while holding the board parallel to the span. Whether it's foam, microfill, primer, or paint.
You'll notice the cut isn't a perfect cut. It's got a little low spot right in here and another little dimple right in here. I don't see anything on the bottom. Looks pretty good. We're not going to worry about that too much because we're going to fill that with some microballoon and epoxy, with a microballoon and epoxy paste just before we lay up the fiberglass on this unit. So let's go ahead and get ready to do a little layup on it. Okay, this little box right here is a box that I built around the epoxy pump just to keep the epoxy and the hardener warm. Let's see if we've got enough hardener in here to do the job. Yes, we do. Enough resin in there, it's okay. The epoxy pump mixes the epoxy in a ratio of 44 parts of hardener to 100 parts of epoxy. It's pretty standard. This epoxy we're using on this job is safety epoxy, sold through Aircraft Spruce and Specialty Company and many others. The first step is to pump a little out. This should be metered. Yes, it's coming out on through both of these tubes. And what I'm doing is I'm going to mix up epoxy to make a microballoon and epoxy paste. It's the first step in the layup over foam. You have to make sure when you're mixing epoxy that you get the epoxy well mixed. You have to actually physically place a hardener molecule right next to the resin molecule, or it won't get completely hard. It ruins the physical properties of the epoxy unless you get it well mixed. The next step is going to be to put some of this white dust in there, and that white powder is microballoons. Pretty nifty looking stuff. You're not supposed to breathe this, so I'm going to put my dust mask on here. There's no special ratio for mixing up a paste like this. Let me put that up there while I put this on. I think I'm going to mix this right over here, Brent. Okay, that looks about right. Max, if you'll go ahead and get rid of this stuff here and straighten this up so we're ready to go.
Max has helped Mike for years on a wide range of projects, but he has very little experience with hot wiring or laminating with epoxy. Max is, in real life, a very talented musician who just happens to like airplanes. Mike and Max didn't rehearse any of this demonstration, so you can get a better idea how this might go in your own shop with your friends. And to make it a little more realistic, they're going to run this sequence without cutting anything out, so you can see everything that happens in real time. So, if you haven't seen this done before, we invite you to sit back and watch us make airplane parts for a while. If you have seen it done, you may want to fast forward for a bit.
Looking good. The idea, let me get this mask off here, I don't need it now. The idea of the microballoon paste is that it fills the, want to go ahead and start on some of that next? Here's a squeegee. The idea is that the microballoon paste fills the little voids in the foam, the little holes in the foam, and keeps the epoxy that we're going to put over it when we lay up the fiberglass from being absorbed by the foam. And I have a technique that I like to use on this kind of stuff. I put it on in one direction and I take off the excess in another direction. Hey, looks like we mixed up about the right amount too. You remember that little low spot right in here I said was going to be filled by the microballoon and epoxy paste. It's right along in here, and sure enough, we are going to fill that. Fun, huh, Max?
Oh, you bet.
And go all the way around the leading edge, Max, down to about an inch or so beyond it. Now, if we were making a wing here, generally we would lay up to about an inch below the leading edge, right down to about there. And the layup that we do on the bottom then would overlap that by about an inch. So it'd be a 1-inch overlap here.
The reason this method of construction works well for laminar flow wings is because the fiberglass skins will be supported by this foam core. The skins will be uniformly stable, and they will be able to maintain a wave-free surface better than most other kinds of construction.
Max and I are trying to work fairly fast. It's a general rule with epoxy and with the polyester resin that you want to work as quickly as you can. When we start to do the layup, you'll see that when we are wetting out the fiberglass, we're going to be interested in getting this epoxy that we've just mixed into the fiberglass as quickly as possible, because the epoxy is thickening up all the while that as soon as we start to mix it, it starts to thicken. And we want to get it in the fiberglass before it's too thick to penetrate the fiberglass. So everything goes better if we go quickly. Okay, we've got the microballoons and epoxy all over the surface. Now we're going to start taking off the excess.
Airframes made of foam and fiberglass tend to be heavy, so great care must be taken at each stage to avoid any extra weight.
It's a little tricky to do this around the leading edge.
Oh.
Okay.
Back in the 70s, very easy and long easy builders were instructed to apply a very thin mixture of micro and epoxy to the foam core with a paintbrush instead of a squeegee. Mike thinks painting it on leaves the surface a little lumpy, and the thinner mixture, because it has more of the heavy epoxy and it weighs more. For these and other reasons, he prefers the thicker micro and the squeegee, even if it does take a while longer.
That's looking pretty good. Okay, Max, if you'll get that fiberglass up here. Oh, thanks, Tim.
So I grab it with these.
This is unidirectional Rutan style fiberglass. It's about, I believe it's 7.5 ounces per square yard. It's unidirectional because most of the bundles of fibers run in one direction, as opposed to a bidirectional fiberglass where the major bundles run in two directions, crosswise. This is pretty standard stuff. It's used on very easy and long easy wings. I think the very easy uses more bidirectional glass than unidirectional. What we're trying to do here is get it very straight, and you notice that we put it on at an angle. This is about 30 degrees from 0, which would run the length of the wing. Okay, Max, if you'll go mix up some more epoxy.
Okay. Scissors.
We had some scissors over here. The red-handled ones?
Red-handled ones. Orange-handled ones.
Ah, there we go. Mix some epoxy now, Max? When I trim a piece of fiberglass, I do just what I learned from working on Burt Rutan designed airplanes. I like to trim it to within 1/4 of an inch of the edge of the surface. And the reason we don't let it hang over any more than that is because the weight of the fiberglass itself will make the fiberglass fall over the edge here, and it will leave a little bubble where it sticks up right next to that edge. I'll show you a little more about that in a minute. This is just one layer of this glass, and before we're through, we'll have another layer running in the opposite direction. Once again, I'm going to trim this edge right to 1/4 of an inch away from the edge. Let me see if I can show you what I mean about this. If I were to leave a big piece of fiberglass laying over that edge there, it would hang down, and you see how that sort of bulges that edge up right there? We want to avoid getting any air along here. Air is the critical thing. Air is what we're trying to get rid of throughout the whole layup. You'll see us spending a lot of time poking at it and fussing with it, and the idea is to get rid of all of the air. We want solid, either fiberglass or epoxy. No air. Air weakens the structure. So we spend a lot of time making sure it lays down flat. Just come on in, Max, when you've got some epoxy. You get some brushes for us, if you will.
There we go.
Okay, I'm going to do a thing here that some folks say is a good idea and others say is not a good idea. I'm pouring it on. There are two ways to put to put epoxy on a piece of fiberglass. One is to just dip the brush in and paint it on, and the other is to get bold and actually do a little pouring. Okay, Max, I think I can finish this off. Will you clean off those squeegees? Clean the micro off those squeegees, and we'll get to squeegeeing this out here.
So I need the acetone for that?
Okay, if you got one of those ready for me, I'll take it now. Thank you, sir. The squeegeeing will even out the epoxy so that we get a nice uniform. The idea here is that we don't want to put any more epoxy on the fiberglass than we absolutely have to. It doesn't increase the strength of the fiberglass. The fiberglass itself is the strong part. And the only thing that the excess epoxy does is add weight, which we do not need. It's a messy job, but it's fun. Notice also that I'm trying to squeegee in the direction of the fibers. If I tried to squeegee against them, it would leave wrinkles and all the rest of that. So I'm trying to keep it going in the same direction as the fibers. Okay, we're going to be ready for some more fiberglass here in a second, Max. Now, on the first layer of fiberglass, we don't have to be too concerned about getting all of the excess epoxy out, because we're going to put another dry layer of fiberglass over the top, and it will soak up some of that excess. Then we can spend a whole bunch of time on the last layer, that second layer, getting the excess resin out. But that's about enough to get us through the first ply here. Okay.
What direction do you want this to go?
The other way. Okay, now this one we're going to run in the opposite direction. Let's see. Yeah, that'll do it.
Hold on the corner and get this straight.
Well, we can lift it up and fix it. Do you want to hang on?
And I guess you don't want to be handling this dry fiberglass with wet gloves, huh?
No. No, what Max is saying is that we've ruined rolls of fiberglass before by picking up the roll with epoxy on our fingers and having it soak into the fiberglass. Once that epoxy is hardened, there's no way to use that piece in another layup. It just will not wet out. Okay. How are we fixed for epoxy, Max? Do we need some more?
We're about got a third of the cup left.
I think we need some more then.
Need some more. Full cup?
Half cup.
Half cup.
Once again, I'm working to try to keep the fibers straight. And by straight, I mean I'm looking at them to see that they are running in a straight line all the way down here. I can see that pretty well. Fiberglass is difficult to see unless you get the light just right. We've noticed when we've tried to take pictures of it for this film, it's almost impossible to see those layers of glass, or those little bundles of glass that I'm talking about. You just have to take my word for it, folks. They're straight. You notice that already in those areas where we had a little extra epoxy on it, it's starting to soak through. Great. Saves me from having to wet it out. This unidirectional glass is tricky stuff because the little pieces keep coming off and making little bundles where we don't want them. But just fight it out. You notice I'm putting on, oh, there's another little bundle. I'm trying to put on as even a layer here as I can of the epoxy. All right. So that we don't have to do any more squeegeeing than is absolutely necessary.
Need more yet?
I think we're going to need a little more. I'm just about out here. Yeah, I'm empty. Perfect timing, Max. You think that? It's good when you're doing a large layup, and this isn't a very large one, to have some assistance around. Again, remembering that you're going to try to get the epoxy into the fiberglass as quickly as possible helps to have someone around to mix and to hand you things and keep your spirits up. The other thing about doing a layup, you notice that I'm not waiting for the fiberglass to soak out to get all dark. I'm just putting it on and moving right on. And the reason I'm doing that is because I've learned that time is essential to allow this stuff to soak up. And if you stand in one place and just tap on it and try to get it to soak up, you're wasting your time. Just put the epoxy down on top of it, walk away and let it soak up a little bit before you come back to it and do the touching up. Well, we've just about done a 2-ply layup here. 2 plies is just what I have on the outside of the fuselage, on the outside of the wings, on the inside of the fuselage sides. It's a pretty standard. It's about the minimum thickness that you can get away with and still be able to handle the structure without poking your fingers through it. 2 plies of this stuff is about 24 thousandths thick. Pretty thin. If you'll take that brush off there for me, Max, thanks. I'll take this. That's starting to look pretty good. Can you see all the little bubbles here, Brent? Can you see these? Okay, let's see what we do with these bubbles here. Oh, they went away. Just one little squeegee got rid of those bubbles. I wonder if you can see these over here, Brent. Well, they're awfully hard to see in this film, but believe me, folks, they're there. Takes a little practice to know just exactly how much epoxy to try to get back out of the layup. It's possible that you can squeegee so hard that you can actually starve the layup. As soon as you walk away from it, it'll suck in some air, which you don't want to have happen. The way I determine how much resin I have in it is by listening to it. If I can run the squeegee down there like that and not hear any bubbles popping, little snapping and crackling and popping, then I know that I've got just about the right amount of epoxy in it. If I run the squeegee down there and I hear them popping and snapping and crackling, even though I can't see them, I know that it needs just a wee bit more resin. But this one is sounding pretty good. It's looking pretty good. And I think we have laid it up pretty much like we wanted to. Now, if we were making a wing, we would trim this off, as I said, about an inch around the corner here, and we would let this side cure and flip the wing over then after it's cured and lay up the other side and overlap it an inch up on this side, so we would have a 1-inch overlap right in here, and that would be about it. What do you think? Okay, but just before we finish this thing off here tonight, I was looking at this corner here. Let me see if I can show you how we would carve a wing tip here. Let's just assume that we wanted to make a wing tip that looked something like this. This stuff is so easy to work with. It's actually a lot of fun. Okay, that gives us the rough outline there. And you can do a lot of roughing out with this little keyhole saw. You can use all sorts of tools. This is one of these. It's a Stanley Surfoam, or Surefoam, or Sureform. Now what we're doing here is just roughing out a shape. I love this. This is fun. Now, I make lots of different kinds of sanding tools. Here's one I like a lot. It's just a paint stick with some 36 grit paper glued to one side and a little 80 grit glued on the other side. And for final work, now, I'm not going to try to make this a beautiful job, but from here on out, I would be very careful to sand in the same direction. What I'm trying to do is make the sanding stick go across this thing at a 45-degree angle. This would be 0, and this is 45 degrees. But you can get the idea. Alright, when I've got it roughly the shape I want it, then I'm going to flip the stick over so that I'm using the 80 grit side instead of the 36 grit side, and that will smooth it out. Again, I'm being careful to keep the sanding at a 45-degree angle. And what this doing it at a 45-degree angle does, it helps the contour. It's a little difficult to explain, but if you do it for a while, you'll discover. And I'm going to go back over it at a 45-degree angle the other way. And as you can see, that's starting to look like a shape. Okay, well that's about it. That's enough at least to give you an idea. That would just be glassed in the same way everything else was, and that would be a wingtip or a wing root fairing or anything else.
At room temperature, safety epoxy cures enough overnight to trim and handle, but it doesn't develop its full strength for months unless the temperature is elevated. At 160 degrees Fahrenheit, for example, it will cure to its ultimate strength in just a few hours.
There we go, hard as a rock. You'll notice today we've got some wood on here. What we've done is we've found some old scrap lumber. We've laid it down on top of this panel, and we've bondoed the ends of it here very thoroughly, and bondoed the long strips to the fiberglass with just these little blobs of Bondo. The reason we haven't put any more than that on there is we want to be able to get this apparatus back off again. And the reason we've put this setup on top of this panel is because we're going to show you how to make a sandwich panel. Forget now that this is a wing. We're going to put this thing up here, and cut this panel again so that we leave 1/4 of an inch of foam up here. You pop this little thing off so we can get the hot wire through it. Let me just stick this up here. Max has already got his fixed up down there on the other end. Ordinarily, if I was making a sandwich panel like this, I would make up another template that was perfectly set up so that it would give us the distance along here, the 0.4 inches that we're looking for. But in this case, we're going to cheat and use the original template. I'm about ready. Max, you about ready to do a little hot wire cutting?
Yeah.
We have this wood up on top of here because as soon as we make this hot wire cut and remove this piece from the top of this piece of foam here, this is going to be very wiggly. And we want this wood to keep it from twisting or deforming in any way until we get the second half of the sandwich, that fiberglass piece that's going to go along this edge here, on. Then it'll be stiff, it won't warp anymore. But until then we have to keep it rigid. Okay, Max, here we go. About 20 should do it. We're going to start back here at about 12. Right straight down. As soon as you're down, let me know.
Down.
Okay, come on back. Half.
I'm at half.
11.
Not yet. 11.
10 and a half. 10.
Polystyrene is the only kind of foam generally used for hot wiring. Urethane gives off very toxic fumes when it burns, and polyvinyl chloride doesn't cut very well.
8 and a half.
The 2 pound per cubic foot density styrofoam we're using cuts well and seems fine structurally, but we don't know of anyone else who's using it to make thin, curved sandwich panels like these. If some unforeseen problem should develop in service, Mike intends to pass that information along. But after 75 flight hours to date, the AR-5 airframe shows no signs of deterioration.
5 and a half.
5 and a half.
5.
5. 4 and a half.
5 and a half.
4.
4.
3 and a half.
3.
3.
2 and
2 and a half.
2.
2. 1 and a half. 1. Right out the bottom. Right straight down. Okay. Fun. Max, if you'll lose the weights and pull the foam out from under here when I take this off.
Wait.
There it is. See if I can show you how flexible this is. Can you see it moving? Nothing to it at all until we get this second piece of plywood over, second piece of fiberglass over it. Very flexible. Tim, have you got any micro for us?
Sure, yes, sir.
Ah. Okay, I guess you know what's going to happen now. We're going to glove up here and do another layup. Ah, good micro, Tim. Now this panel could represent the panels that we put that we used on the sides of the fuselage, or on the tail cone of the fuselage, or on that upper deck we showed you earlier. All the same kind of construction. Tim, I wonder if you could get that hot wire saw out of here. Boy, it helps to have people around. Okay, Max, we're just about ready for glass here. If you want to go and pick that up, I'll finish this off. Take a couple more swipes at it here.
Are we going to get up under here?
No. Okay. Tim is mixing up some epoxy for us. This is bidirectional. The stuff we put on the other side is unidirectional, and this stuff we're using on the inside here, because we don't need as much fiberglass on the inside. We'll need one more of these, Max.
Right.
We don't need as much fiberglass on the inside. Remember, I mentioned that on the outside we need about 24 thousandths thick fiberglass laminate, because any less than that, we'll have trouble with people poking their fingers through it. But on the inside here, we don't have to worry too much about that, because nobody's going to be in here. This, remember, is the inside of the airplane, and the only person who's going to be poking around will be the builder, and he should know better than to poke. Okay, we're ready for some epoxy. Thanks, Tim. I'm just going to work my way toward you, Max. We're only going to put one ply on here. This is fairly representative of what I've done on the inside of the AR-5. You notice that when we reached the end of that first piece of fiberglass, we overlapped it about an inch. That's just about all you have to do. It will act in terms of strength just about as if it were all one piece of glass. So you, in theory, could make an airplane out of scraps, and it would be strong enough. The only problem would be that you'd have it full of double thickness overlaps, which would add weight. So it's better, really, if you can cut a piece of glass that will do the whole thing, not have to make it up out of little pieces. Tim, I think we're going to need just a wee bit more epoxy.
I think you're right.
Let me take the rest of this, Max.
About half of that?
Yeah. Or a third. About 5 pumps, Tim, will do it. And probably by the time you're finished with that mixing, Tim, we'll have decided that we've got enough on here. No, we do need some more. And the squeegeeing, just like we did on the other side. Micro is not stuff you want to mix up into the epoxy, because the micro balloons actually weaken the epoxy a little bit. They're just hollow glass spheres, and you don't want to contaminate the epoxy that you're laminating with micro. That's why you saw me being careful about getting the micro off the squeegee. How you doing over there? You got any?
Looks like we're short.
Not too bad though. Boy, that's close. We may make it here. As a matter of fact, it looks like we've got it. Sorry, Tim.
Put it back in.
Okay, put it back in the pump. No, he's just kidding. He's just kidding. Okay, now I'm going to go over the whole thing and get the excess out. Not too much excess here.
The average layup over foam like this will yield a ratio of epoxy to fiberglass by weight of about 50-50. Half epoxy, half glass. Leave a little extra epoxy on, or take a little too much off, and the ratio will change. The difference between too much and too little on the AR5 might amount to around 12 pounds. That doesn't sound like much, but on an airplane this small, it's significant. So it's well worth spending a little extra time on this important step.
There it is.
Because this panel is curved in one plane only, it's not a compound curve. It could be made in a variety of other ways with other materials. When we look later at construction of the fuel tank, you'll see another method for making curved panels that certainly could be used on that deck, for example. And it might even work for the tail cone. Mike chose this particular method because he believes it produces the lightest sandwich, and because styrofoam is the least unpleasant foam to sand and work with. The dust from urethane foam is particularly irritating to eyes and noses, and urethane doesn't appear to hold up well in service. Polyvinyl chloride, or PVC foam, has a large cell structure that requires a lot of micro to seal, and it doesn't sand well, at all.
Well, here we are. Finished panel. Max, you want to get on one end of that thing and just fairly stiff stuff. Let's see what we weigh here. This is pretty typical of the panels throughout the airplane. About 1.5 pounds, a little less than 1.5 pounds it looks like.
That's right.
Before we're through with this panel, I want to show you one more thing. How we attach bulkheads and how we tape things together. I've cut a little piece off of this that I'm going to use as a bulkhead. Just assume that this is the instrument panel or the rear seat bulkhead. You notice that I've sanded this part of it right here. I'm going to do the same thing to this part. You have to sand epoxy before you can bond it with epoxy again. The epoxy, when it cures, forms a film that has to be abraded before you can get a good bond. So this is very typical of what we would do on any bonding surface. This is 36 grit sandpaper. And you notice that I'm not wearing a mask here, which I normally do. I'm not this silly all the time. I'm doing this so that I can talk to you folks. And what I want to show you is a taping method that I've been using for years. This is a piece of polyethylene plastic. It's 2 mils thick. That's quite thin. And I'm just going to pour some epoxy on this piece of bidirectional fiberglass that we've cut. And I'm going to close put the other piece of stuff down here, and I'm going to sneak past you and get this. I'm just spreading the epoxy out here. We're going to let it soak into this piece of glass between the two pieces of plastic. And while that's soaking, I'm going to bond or sample bulkhead with micro. This is thicker micro than we mixed up last time. Just added some more micro to the epoxy to make it thicker. And you'll notice that I'm making a pyramid here. Let me show you what I mean by that. Can you see that we've formed it into a little peak, a little mountain on the top? The idea of that is to avoid us trapping any air when I stick this down on the surface. And here it goes. Micro is fairly stiff stuff, so it's going to hold that thing upright. I've got a stick here that I've made a very small radius on, and I'm going to use that radius to form a little radius in that corner built up out of micro. And the reason I'm forming this little radius in the corner is that the fiberglass that's going to be put into this corner won't make a very sharp corner by itself, and it will tend to bridge across that sharp corner unless we fill it up with micro. And we don't want it to bridge because we don't want any air down in there. Now back to this. I'm squeegeeing out the excess epoxy. That's enough. And I'm going to cut a little strip out of here. This strip is going to be about 1.5 inches wide. I want about 3/4 of an inch to lap up on both edges, both the bulkhead and the panel. Before I go any farther, I'm going to put my gloves on here.
Mike worked out this taping method in 1978 while working at Fred Duran's glider repair station in Mojave. Some very easy and long easy builders have used it since with good results. It produces a nice, neat job without a lot of mess and loose ends.
What I'm going to do is strip one side of this off. It's a little tricky to do if you got a big thick pair of gloves on, but I think we can manage. One piece of the polyethylene plastic is coming off, and I'm going to fold this in such a way that I can stick it right down in that corner. There it goes. I've stuck it in there, so, and I've forced all of the air out in that corner with the paintbrush. Now I'm going to pop the other side of the polyethylene plastic off. And get rid of it. And then spend the rest of my time making sure that all the air is out of the tape here. This, as I said, is how the whole airplane is put together, with micro gluing the foam to the surface and tape, fiberglass tape, gluing the fiberglass edges together.
And now that we know all about composites, let's finish looking at the airplane.
Tim, would you take this? Okay, now let me come around here. We want to take the canopy off next. We blew the canopy out of 1/10 inch plexiglass. It's very thin, so it's light. The inside is a sandwich around in this area. It's just a styrofoam sandwich. This is all unsandwiched. It's just 4 plies of bidirectional glass. Tim, would you take this for me? While we're here, let's take a look at what's underneath here. That's the flap control bell crank. Nice solid clunk. As long as we're looking at the flap control bell crank, let's look at the flap itself. You'll notice that the gap along here is certainly nothing spectacular. It's a 1/16 of an inch to a 32nd of an inch. That's pretty typical throughout the airplane. It's also true for the aileron. And let me show you how that aileron is made, and then we'll flip the wing over and take a look at the bottom side.
The ailerons, like all the control surfaces on the airplane, are hot wired from styrofoam. The odd shape at the trailing edge is to stiffen it until it's glassed. Then it's removed. In the middle of their spans, the aileron cores are notched. Those are hard points made of plywood with nut plates behind them. They're bonded to the cores to support the actuator pushrod brackets. A short support spar is laid up, the wet glass being pressed down over screws with sharpened heads. Some of the notched portions of foam are then reinstalled with micro. And finally, sheet aluminum hinge reinforcements are bonded onto the foam cores. All the control surfaces are hinged in the same way, except for the rudder. It's hinged in 2 places. At the top, this pin on the stabilizer fits into this bushing mounted in the rudder. The other hinge is here on the bottom. It's made of welded steel. All the rest of the control surfaces have piano-type hinges riveted over those aluminum plates we bonded to the cores. The hinges have nut plates installed behind them and are fastened to the wing or stabilizer with number 6 screws. But let's finish looking at the construction of that aileron. The foam cores are glassed on top and allowed to cure. Then they're flipped over and glassed on the bottom. The flaps and elevators and rudder are all made the same way, except that they are all actuated from their ends rather than from their middles like the aileron. This is a flap with its plywood hardpoint, with the stub spar coming off the backside of the attachment point. It's glassed in the same way that the aileron was, and then flipped over and glassed again. And the reinforcements are applied to the flap actuator attach point.
Okay, here we are with the wing upside down. Here's the flap actuator. There's the flaps. I got a little piece of foam in here to keep the flap from going too far. It's a push rod actuation. It comes right off the bell crank there. And I want to show you the gaps. Nothing fancy about any of this stuff. These are the sorts of gaps that you'd find on any home-built composite airplane. I didn't seal any of these gaps anywhere on the airplane. You'll notice that we're using washer head screws. We haven't countersunk these. The main reason I didn't do that was I would have had to make this piece of fiberglass that we're countersinking, or that we would be countersinking, 1/8 of an inch thick to really get a countersunk screw into it. We didn't want to do that, and I don't think there's a lot of drag penalty back this far on the airfoil anyway. So, washer head screws. There are 3 hinges on all of the surfaces. And here's the aileron. You'll see that the gaps here are just about what you'd expect to find on any well-made composite airplane. Has a horn balance. This is 100% balanced surface, as are all of them on the airplane. Let's go back over here to the center here and talk about this actuator. This is a push rod actuator. Runs through the aft spar here, up forward here. Let me pop off this door and I'll show you what's inside there. Okay, there's the push rod, and this is the bell crank. Let's see if I can make it move here. They're cable operated ailerons. This is 3/32 cable, and there's the pitot tube. And if we can move on down here, I want to talk a little about the landing gear that Max is holding up for us. Here's where the landing gear bent. And if you'll pull that out here for us, Max, we'll see how that's mounted here. It's just basically bolted to the front face of the spar here. And I was very pleased to see that there was no damage to the spar. The landing gear failed, but the wing did not. So this unit is just about ready to accept a new landing gear. This is the only damage to the wing right here, a little superficial cosmetic work here. And that about covers the wing on the bottom.
Okay, let's take a little closer look at the landing gear while we have it here on the bench. The design for the landing gear came from an article by Tony Bingelis in Sport Aviation magazine in April of 1976. Very interesting article. Tony, I understand, has written a book, and I'm pretty sure that all of this stuff you can find in Tony's book, advertised in the back of Aircraft Spruce and Specialty Company magazine. The wheel and brake assembly are from a BD5. It's a 4-inch diameter aluminum wheel, split hub. It's a 410 by 4 industrial tire, not for highway use. And the brake is a 2-puck brake assembly that pushes against the disc here. It seems to work very well. It's just about right for my own airplane. The axle snapped off right here. It used to be mounted right over this little stub insert here. It pulled the whole works off when it broke. And Max, if you'll take that. The first damage you see is the damage to the wheel pant bracket here. It just got basically bent up. Not too badly damaged. The gear is a tube inside a tube telescoping gear. These are of course made up of square tube and scissors. This bolt right here is a bolt that restrains the gear from coming all the way out. And the tube here works its way up into this tube to about that far. From here on up to about here, it's a coil spring, and from here on up to the weldment at the attach point is there's a wooden dowel that just basically supports the back end of the compression spring here. Let's take a look at this one and we'll see what the weldment at the top looks like here. We just spin it around. It's pretty self-explanatory. It's a 4-bolt pattern here with 4 1/4-inch bolts that bolt right into the front of the spar. Okay, Max, if you'll take this. Here's the gear leg fairing, just a piece of fiberglass. It fits over the gear leg by springing it open and working it right over the leg. These brackets here accept the soft aluminum pop rivets. We just drill them out when we have to take the fairing off. And finally, the wheel pant. Took a little bit of a beating, but it's repairable. Just a pretty standard unit made of fiberglass.
Since 1978, Mike has supported himself with fiberglass, working on a number of interesting composite projects, using a variety of construction methods and materials, from the Avtech 400 with molded Kevlar and honeycomb, to the Moeller M400 with moldless prototype construction. Mike found planking with urethane foam and hand carving works well on bodies with compound curves, but it's not something you can do well without a good eye and a lot of practice. Hot wiring would be easier, of course, but you can't make compound curves with a hot wire. Only straight lines. That's why hot wiring was only used on wings, at least until the AR-5.
We've spent a lot of time in the aerodynamic film talking about how we arrived at this particular shape, especially down here at the wing root. One of the things that comes out of this particular shape is the ability to use a unique kind of construction method. You notice from the trailing edge forward, from the trailing edge of the wing forward, all these lines are straight lines. Even the upper deck and the lower deck are straight lines up to the firewall. From about the trailing edge back about a foot, it's a compound curve, and then from here all the way back to the tail, they're straight lines again. Straight lines, straight lines, straight lines, even up the bottom of the fuselage is straight lines. Now what all these straight lines have allowed us to do is cut this fuselage with a hot wire, just like we did with the wing.
And here's how it works. The sides of the fuselage, from the firewall back to the seat back bulkhead, are cut out of 1-inch thick styrofoam. The wooden stringers that will become cockpit rails are pre-bent and bonded to the edges of the foam, and fiberglass is laid up on the inside faces. The two sides are then bonded and taped to the firewall, instrument panel, and rear seat bulkhead. The assembly is upside down here while it's curing. It's then turned upright and jigged into position on the bench, and hot wire templates are bondoed into place. The tail cone is then planked with styrofoam, secured with beads of urethane spray can foam on the inside, and then the tail cone and forward deck are hot wired. It's sanded where the tail cone joins the flat sides to blend and remove the rough spots, and the canopy frame is foamed up out of styrofoam blocks, again secured on the inside with urethane spray can foam, and carved just like we did the wingtip to fare into the canopy. After final sanding and shaping, the whole thing is glassed. As soon as it's cured, boards are bondoed to the canopy frame to hold its shape, and the canopy and its frame are removed. Same thing for the right and left halves of the tail cone. It seems like we're going backward here, but we're not. The tail cone halves need to be hot wired to correct core thickness and glassed on the inside. The upper deck is likewise hot wired and glassed. The panel under the fuel tank was hand carved out of urethane because it's fuel resistant. The two tail cone halves are then bonded and taped together and aligned on the bench so the vertical and horizontal tail surfaces can be installed. The fairing is carved and glassed, and the bulkheads are installed. The whole works is then reattached to the fuselage and taped together. The fuselage is then mated with the wing. Fairings are made at the roots. The cowling is carved from urethane pour foam and glassed. And the whole airplane is covered with a micro balloon and epoxy paste and sanded smooth. A polyester primer surfacer is sprayed on, and the airframe is sanded and painted with Imron polyurethane.
Okay, we've finally reached the point where we can take a look inside the airplane here to see what damage might have been done by this incident, as the FAA calls it. First thing we want to look at is the motor mount brackets on the back side of the firewall. The firewall is just a piece of 1/4-inch plywood. It has a doubler here where the motor mount bracket bolts to it, and this is a piece of 1/8-inch plywood. Well, we're looking for damage all around this area here. Let's take a look at this one over here, and we'll show you a little more what we're talking about. We're looking at the fiberglass area that might be damaged around in this area here, and we're looking, of course, at this stringer. This stringer is made out of fiberglass with high-density polyvinyl chloride foam, and of course we want to look down at the bottom to see what's going on down there. There's another stringer, and down below it there is the rudder pedal, and just behind the rudder pedal we'll take a look at that.
There's the back of the motor mount bracket. There's no sign of damage to the fiberglass in the corners or to the stringers. We pronounced it ready for flight.
Okay, let's take a look at the fuel tank while we're in here. This is the tube that runs through which I run all the electrical wires and the throttle cable. And this little unit up in here is a scupper, just for spilled fuel around the cap. It drains out through this hole here. And we'll show you how this fuel tank is made.
The tank is made of 1/4 inch thick Clark foam, glass on both sides, and assembled by bonding and taping. Before the bottom is installed, the curved top is made by glassing one side of the foam and bending it in place, and then glassing the outside. The top is then removed and the fuel filler neck is installed. The top is then duct taped on the inside and temporarily reinstalled, so that a tape flange can be laid up through the still open bottom. The bottom is then installed, and the vent, baffle, sump, fuel gauge mount, and the conduit for the wiring and throttle cable are glassed in. The top is then bonded to its flange and taped all the way around. The tank holds 12 gallons, which gives the AR-5 a 500-mile range with 45 minutes reserve.
Now that we've looked at the fuel tank, this is the back side, of course, of the instrument panel. There's nothing much to say about it. We'll show you the front side in just a second. All right, here we are in the cockpit. Let me take the seat out so we can take a good look in here. That's just a foam pad. And the seat back, standard fiberglass and foam sandwich. This is a piece of 1-inch foam. We've built it up a little bit behind here so that it conforms to the shape of my back. And up in the far left corner up in here, we have the instrument panel with the first of the instruments. This is an exhaust gas temperature, dual exhaust gas temperature. And to the right we have the famous backward throttle, pull for full throttle and push for idle. And a primer, so just a normal little pump. We have water temperature. We normally run in the 180 to 185 area for hot days and 165 to 175 for cold days. Standard RPM indicator. So we run about 6,500 to 6,650 at full throttle, and I cruise around 5 to 5,800. Starter switch. Ignition. You notice we don't have provisions for the dual ignition that we've recently put in the airplane with the 582. We'll get around to that one of these days. You know what this is. Airspeed indicator. Took this out of an old Cessna. And a standard altimeter. Whoops, we're reading a little low here. And to the far right, regular fluid compass. Down below it, we have KX99 Bendix King radio. It comes out quite easily. And the stick. Here's the microphone switch on the stick, and you'll notice that the stick, we'll show you that assembly in a minute, passes the elevator push rod through this bulkhead here and runs it all the way back to the elevator. Notice that the pilot sits on the center section of the wing. This is the main spar here. The instrument panel really is a ring bulkhead. The forward side here is where the bolt goes through that attaches the bulkhead to the forward side of the spar. The other one goes through over in this area. And that about covers that. On the left side of the cockpit, you can see the canopy latch, straight rattan style. Thanks, Bert. And down here, the flap handle. It's a 2-position flap, or 3 if you count all the way down. And the torque tube, of course, behind the seat that carries that torque over to the bell crank on the right flap and the bell crank on the left flap. Let's do that one more time and look at the flaps.
And as long as we're here, let's see how that shiny wing is made. Wing construction starts with large styrofoam blocks bonded together with urethane pour foam. The airfoils are hot wired. Then the front and rear spars are cut and the leading edge is hot wired a second time to make it hollow for control runs and plumbing. Because the hot wire works best on spans of 5 feet or less, each wing core is made in 2 pieces that are then bonded together at mid-span. The hollow leading edges are fiberglass on the inside with 1 ply of bidirectional glass. And 4 fiberglass and foam ribs are installed to carry the shear loads. Plywood hardpoints are bonded in place at the front spar to provide support for the aileron bell cranks. And the wing is cut in 2 places behind the landing gear attach points, and aluminum hardpoints with nut plates are bonded in place. And fiberglass ribs are laid up over them with unidirectional cap strips. The wing cores are then reassembled and bonded together. And another reinforcement for the landing gear is laid up on the main spar web. The center section is dished out to form the seat bottom, and the stub spar is installed to reinforce the spar cap at the seat. Aluminum and plywood hardpoints are bonded to all 4 corners to receive the 7/16 inch diameter wing attachment bolts. And finally, root ribs are laid up on the sides of the center section and wrapped around over the hardpoints at the front and rear. The whole works is then jigged up and bonded together. The black things are weights to hold it down flat. The rear spar at the center section is laid up. Its outboard ends will be finished later. At the front, the C-section main spar is laid up with a bidirectional glass web, with the major bundles running at plus and minus 45 degrees to the span. After a check to see that the landing gear still fits, the leading edge is carefully jigged and bonded into place. And a spar cap is laid up using 3-inch wide unidirectional E-glass tape, tapering from root to tip. The main spar is similar to the one in the Long Easy. Those are the 2 ribs behind the landing gear attachment point. Then the top of the wing is fiberglass, just as we saw earlier. This is a big layup and has to be done all at once. When it cures, it's flipped over and glassed on the bottom. Foam is removed at the aft of the wing, and the rear spar is completed. And here's the wing ready for the installation of the root ribs. And it's finished. The hollow leading edge is the major difference between this and the Long Easy wing. The vertical and horizontal stabilizers use the same materials and techniques. Now let's finish looking at the fuselage.
Okay, here's the bulkhead that forms the seat back. It serves as, just as the instrument panel does, as the mount to the spar, the aft spar in this case of the wing. bolts go right in through here. The rollover structure here was the last part of the seat back bulkhead to be applied. This is, of course, a shoulder harness attach fitting. It's held with an 1/8" cable that goes back and is anchored back at the ring bulkhead back there. This is just the canopy restraint cable anchor. It's just a piece of wood with a little fiberglass over it and a nut plate back behind. Let's see how this thing is made.
The bulkhead is cut out of 1-inch thick styrofoam and glass on the back side. It's flipped over and foam is removed so the glass applied to the front will make contact directly with the glass on the back side. The edges of the foam are rounded with a stir stick with sandpaper glued to it. Then, fiberglass is laid up on the front side. And the bulkhead is complete. It's now ready to be cleaned up, trimmed, and installed. It's bonded and taped in just like all the rest of the bulkheads in the airplane. And there's that ring bulkhead. Let's see how it's made. The ring bulkhead is cut out of 1/2-inch thick styrofoam and glassed on the back side. The foam is removed around the edges for that glass-to-glass bond. The foam is then beveled as before. This is a Dremel tool with a small disc sander attachment. The corners are rounded with the same type of sanding stick. And the front side is glassed. And that completes the bulkhead, as well as our look inside the airplane.
Well, that pretty much covers how the airplane is built. I hope you've enjoyed taking a look through here. All of these construction techniques are based on stuff that I found in Burt Rutan's moldless composite sandwich home-built aircraft. That's the name of that book, believe it or not. You can find Burt's book in the back of Aircraft Spruce and Specialty Company's catalog. It's well worth reading. And that about takes care of the movie. Hope you found this interesting. We certainly enjoyed making it. And see you in the next video.
Church, armed only with a kitchen knife, a crosscut saw, and some sandpaper, Mike creates the master patterns for a state-of-the-art Formula One air racer. Starting with a pencil drawing and a small foam model, he covers the lofting of full-size cross-sections, the carving and finishing of the plug, and finally, the assembly of the airplane with its finished molded fuselage. Making fiberglass molds chronicles the development of a 6-part molded fiberglass cargo pod. It shows all the design and fabrication techniques used to produce low-cost, professional quality production molds. Every step is explained, from first sketches, through master patterns, to male and female molds with offsets and joggles, to finished parts.